We're looking at a guy by the name of Dean Potter right here. Dean was an outdoor stuntsman, if you will. He was a base jumper, a world class climber, and here he's seen tight roping across the Yosemite Valley out in south central California. So if we look at Dean here, Dean's got an equal probability of falling to his right or to his left of this tightrope if he loses his balance. So here's the thing. If Dean doesn't stay perfectly balanced, then he's going to fall to one side or the other. In chemical reactions, we have to be perfectly balanced in that our number of atoms on the product side has to equal the reactant side. So that's what we're going to look at today. So a quick recap, we have physical properties where a substance has physical characteristics. Okay, so like density, color change, excuse me, not color change, just color, texture. Chemical properties are properties that we only see when that substance mixes with another, reacts with another. So in the case of our cabbage juice, well, a physical property of the cabbage juice would be that it was bluish in color. But in the case of our lab the other day, when we mixed that cabbage juice with the ammonia, it became green. So a chemical property was that it changes color in the presence of an acid or a base. And you don't see that unless you put it in with an acid or a base. If it's just sitting there by itself, you're not going to observe this. So that's what a chemical property is. Physical changes are when a substance can undergo a change in appearance while retaining its same chemical components. So no bonds are broken or made. Whereas in chemical changes, the bonds of a substance are broken and new bonds, new different bonds are formed between other atoms to make new substances. And that's what we're going to look at today. What we're going to be doing is called balancing equations, and we're doing that to demonstrate the conservation of mass in chemical reactions, which means you got to have the same number of reactants as you do on the products. In this case, we have a little example here that we have 14 grams of iron and 8 grams of sulfur. Well, 14 plus 8 is equal to 22, so we have to have no more or less than 22 grams of iron sulfide made from this equation. Now this measures it in grams. What we're going to be doing is measuring atoms. But the theme here is that atoms aren't created or destroyed in chemical reactions. The bonds are only broken and they are rearranged between atoms of different combinations. So here's what we're going to do today. What we need to do is make sure we have the same number of atoms on the reactant side versus the product side. So we do this by adding something called a coefficient. A coefficient is different from a little subscript because these are big numbers placed before a chemical formula in an equation. Now, in this case, what we're looking at is H2 plus O2 plus H2O. Well, automatically, we already have one of each of these if we haven't balanced it at all. If we didn't have a coefficient at all, it would still mean that we have one of them. If we had 0 of any of these, we wouldn't have written them in the first place. So bottom line is if you have to put you can put a 1, I'm not going to count it wrong. You don't need to put a 1 in front of a coefficient if it's already there. So let's take stock of our current number of atoms. If we separate our product side from the reactant side, we need to count our hydrogen atoms and our oxygen atoms. How many hydrogen atoms do we have? 2. So hydrogen on the product side, excuse me, the reactant side, we have 2. How many oxygens do we have? 2. Okay, now we go to the product side. How many hydrogens do we have? 2. Looking good. How many oxygens do we have? 1. Because there's no subscript there. So our problem is that 1 does not equal 2. So we need to boost our products. The way we have to do that is we cannot add a subscript. We can't do that. You can't just put a 2 after this and say, okay, we're good, because you have to make new bonds that you don't have available. So you cannot do that. What you can do is you can put a big number before it. So if we put a big 2 in front of it, let's make this red. If we put a big 2 in front of it, that means, yes, now we do have 2 oxygens. Okay? But a coefficient applies to all atoms that it comes before. So it makes 2 oxygens, but it also means that we now have 2 times 2 hydrogens, which is equal to 4. Okay? What this means is that, if you're having trouble visualizing this, let's draw this out here. 2 H2Os, if we wrote that back, we would have H2O, H2O. So what this means is that we have 1, 2, 3, 4 hydrogens. So anytime you put a coefficient in front of an element that has a subscript next to it, like this guy, so we have our little subscript here, we have our coefficient. That means these guys are multiplied by each other to get the total number of hydrogen atoms. So 2 times 2 is 4 hydrogens. We have 4 hydrogens, we have 2 oxygens. Okay, so now we got to take a look at our other side. If we zoom out a little bit and look at our reactant side, we have 2 hydrogens over here, but we have 4 on the products. So here's our 2, here's our 4. That's our problem. So what can we do? Well, we're lucky because it's just H2 here. So if we clean this up and we put a coefficient of 2 before H2, now how many do we have? We have 4. And we still have 2 oxygens because we don't need to put a coefficient before that. So that is equal to 2. So we are now balanced. So our coefficients would be 2, 1, and 2. Again, writing a 1 here is optional. You don't need to do that. And here's our finished equation right here. So all we're doing today is balancing out the individual atoms of an element on the reactant side versus the product side. So we're going to be practicing that for class today.